All right. How we all doing tonight? You guys can hear me okay? Okay. Um, couple of bookkeeping things at the beginning. Um, this is the last meeting of week 2, which means you're now just about 40% of the way through the class. Um, I have graded and sent back your first homeworks. So if you did not get an email from me saying, here's your graded first homework, I did not get your first homework. So a lot of people I did not get your first homework from. I'm counting 1, 2, 3, 4, 5, 6 people. Um, I don't have a grade for. A few people I don't have the lab from either. Remember, you got to hand in the lab every week. So do check your email and see if you did the homework or if you did meant to send it but didn't or something like that. Do make sure you do the labs. They're graded as well, mostly for correctness. I mean, mostly for completion. So if when I write you back corrections on stuff in the lab, that doesn't mean it's wrong and you're losing points. It means, hey, this is stuff that you're doing wrong in the lab to think about and fix for the homework. Okay, that's why I think it's important that you do the lab first and you give yourself time for me to respond to the lab you send in, because I'm going to try to give you hints on things you're doing wrong so that you can do the homework better. Okay, so any questions on that? On what's going on? If you think you should have sent me a homework and didn't get an email back today, then I didn't get it, so send it again. Um, okay. So this week is the machine language lab. Um, somebody was one, at least one person, maybe more, had trouble logging on to the um, machine language program system. I put the files on Blackboard. Um, it's a zip folder, so you pull out the whole zip folder and um, put it someplace in your directory. If you're on a PC, what you want to do is run I think it's called run bmachine dot bat. Whoops, run bmachine dot bat file. Um, that'll work on a Windows machine. It's a Windows script to run um, the file. If that doesn't work, or you're on a Mac, you can try double clicking there's a file in that folder called compiler.class. Um, that's the one you want to click to run. If setting the security settings doesn't work and loading it from the web page doesn't work. So any of those ways should eventually get you in to running the compiler. Just a reminder of what it looks like if you haven't seen it yet. Let me bring up my copy of it. This is what should pop up when it runs. Hopefully you guys can see this. It's kind of the greenish screen with the stuff on it. And so if this pops up, you're good to go. Sometimes it takes a minute or two to pop up. If it doesn't pop up from loading the web page, then try using the files on the Blackboard or some other way. Again, the lab is long. If you started it, you know. And so you want to give yourself time to get through the crappy procedurally stuff of making sure you can run the program before you get to the beginning of the lab, and then give yourself time to work your way through the lab, because it's not easy stuff, and it's a lot of different stuff. Okay, so any questions on running it, on running the program or anything like that? Hopefully you all can run it okay. If you can't, let me know and we'll figure something out. Any questions on things you're stuck on doing the lab, things you want me to explain about what the lab's asking you for, or what the machine language is making you do, or anything like that? All good. I'm worried that nobody's having problems. That either means people haven't started or something else is going on. Because, again, this is not the easiest thing in the world. So just a couple of things to keep in mind about this. Let me get back to my drawing program. Come back here, you. Okay. So things to keep in mind. When dealing with the machine language. First of all, remember that what you're seeing is two things. So when you get the giant window is split into two parts. In this part, it has all the numbers going up by twos with the little boxes. This is the stuff kind of on the green side, on the left, on the right. And then on the right, it's got 16, well 17 if you count the program counter, little smaller boxes down to F, where F is number 16. So what you're seeing is on this side, you're seeing memory. Okay, that's the simulation of the memory chip of what's going on. On this side, you're seeing the registers. Okay, so remember that we talked about this last time. Registers are special memory locations that exist inside the processor. Most instructions use registers. In fact, I'm pretty sure that I can't think of any instruction that you're going to use in the labs or on the homework, with the exception of the C instruction that stops the whole program. Every other instruction uses a register somehow. So they're very, very central to how the processor does things. The hardware reason for this is that the registers are built for speed. They're optimized as part of the processor, so the instructions in the machine language are made to do things directly with these registers for speed reasons. And on the other side, oops, what did I just do? Memory holds data that is meant to be kept for a while. So the idea behind registers, since there's only relatively few of them. Now in the programs that I'm making you write, you don't usually use all of the registers, but the fact that this small dinky machine language only has 16 registers is the part of it that actually is pretty close to how real processors work. A PC has, depends on how you count it, but something like 8 registers. A Mac might have like 32 registers. But the point is, you don't have billions, okay? And you can imagine if I was mean and made you write bigger programs that had to store lots and lots of data, you would pretty quickly run out of registers to hold that stuff. So that's what we have the memory chip for. Memory is, gigabytes of space, so billions of bytes of space. So we can hold lots and lots of stuff in there, way, way, way more than we can hold in the registers. Okay. Memory also holds the program itself. Well, the instructions of the program itself. Okay. So memory is doing two things. One, it's holding some data that your program might need, and two, it's holding the instructions that you write in the machine language in these hexadecimal numbers to get the program to work. Okay. So what pretty much every program I make you write does, both on the lab and on the homework. There's a couple of exceptions, but mainly, what every program I make you write does is, first of all, put some data in memory. This is the information the processor is going to work on to do their stuff. Okay. Um, put some data in memory. Put some instructions in memory, written in machine language. This is at some address I tell you about. So, for example, write a program that reads in two numbers located at addresses 40 and 42 and adds them and stores them at location 44. That's one of the first programs I make you write in the lab. So you put some data in memory, some numbers at locations 40 and 42. You put some instructions in memory written in machine language. These always start at address 0 at the top of the screen, or address 00, I guess, if you want to map it to what it looks like on the screen. Then the program will, first of all, read or load the data from memory into a register. And sometimes I tell you what register to use, and sometimes I say I don't care. All the registers are pretty much the same. Do something to the data you put in the register. So this do something, this is the point of the program. This is what the program's actually doing. This something, adding two numbers or whatever it is. Put a result that you figured out by doing instructions back in memory. Okay, and then you're done. Okay, so let me walk you through an example of this. If you've done the lab, this hopefully will look kind of familiar. If you haven't, hopefully when you do the lab, this will help you make sense of it. So suppose we want to write a program that adds two numbers stored in locations 40 and 42 and puts the sum in location 44. Okay, this is like, I think I make you do this in the lab pretty early. Okay, in English, the steps will be now following the description I just gave you about what in general you're trying to do. The steps will be, first of all, load the number from location 40 into some register. Let's use 0. Why 0? Because it's first. You can pick whichever one you want. Then second, load the number from location 42 into some register. Let's use register 1 for the second one. Why? Because it's second. Again, you could use register 9 and register 3 if you felt like it. Personally, I like using kind of registers from top to bottom in order so I can kind of keep track of what's where. Add the two numbers together and put the result in some register. And again, it doesn't matter which one. And then the last thing we got to do is put that sum back in memory at location 44. So the point of me writing this out in English, first of all, is to make you understand what the machine instructions I'm about to write for you in a minute are going to do. But second of all, because I think this is a process you want to go through. Especially with the longer and harder programs, you want to write down in English the things you want to have happen. Because I think it's much easier to understand the English explanations of what's going on in the program than it will be to understand a whole bunch of weird numbers. Okay, so I think this is a helpful way to break down the problem. And then if you get stuck, you can say, well, I know how to do step 1. I know how to get it out of memory into a register. I know how to do step 2. I know how to get it from memory into a different register. I know how to do step 4. I know how to take a number and throw it into a register. I don't know how to do this. And so if it turns out there's a step you don't know, that's a thing you can look up and try to figure out from looking at the lab or looking at the book. Book's explanation of the instructions are all in the appendix, or by asking me. Okay. But the point is, being able to focus on the one thing you don't know how to do will make your questioning or you're looking for what needs to be fixed, a lot easier than saying, I don't know how to write this program. Okay, the more you can kind of focus in on exactly what you don't know how to do, the more likely you are to get or understand the answer when it shows up. Okay, so anyway, in machine language, the way I write this program in machine language, okay, remember all machine language instructions are 4 hexadecimal digits long. The first hexadecimal digit is the type of the instruction. So the first of the 4 hexadecimal digits is the thing I want you to do. Or the thing you want the computer to do. The rest are different depending on the instruction. And so in the lab, I'm giving you these charts that look like this. The first digit is, let's say, 2. The instruction, let's not use 2, let's use 1, because I'm actually going to use 1 in my program. The instruction is load a value from memory, and the second digit is the register to load into, and the third and fourth digits are the address to load from. So I give you a chart like this that maps out the structure, the parts of every single instruction that you're gonna need to use. So for us, the first thing we had to do was load the data from location 40 into register 0. So that would be 1 is the instruction to load from memory. 0 is the location, the register I'm going to read this into, and 0 is the address in memory I'm getting this from. Okay. Instruction 2 was load from 42 into register 1. And so that would be instruction 1, load from memory. Register 1 is the second digit from spot 42. Okay. Instruction 3, add register 0 and 1, put sum in register 2. The command for add turns out to be instruction 5. The second digit of instruction 5 is where to put what register to put the sum into. and then register 0 and register 1 are the two things I want to add. Okay, and then instruction 4, store sum to location 44. The instruction to store is 3. The second digit of instruction 3 is the register I want to save. The third and fourth digits are the place I want to save it to. And then I forgot to put this in my English algorithm, but there's always C000, which is end the program. So before I go on, any questions on this? Does this either help you understand what's going on or unearth any questions you have about what we're doing here or anything? Because this is a pretty simple program, and as they get harder, I think going through this process is good, but obviously longer and more complicated. So any questions on this level of what I'm trying to make you do with the machine language? Okey doke. I think I'm good. All right. So then what you would do, again, so far I've done this all kind of off to the side on paper. Okay. Then what you would do is you would go to the actual applet, the actual compiler, this thing. Hopefully you can see the blue screen now. And you start typing in the program. Now, remember, the programs start, well, actually, I said the first thing I would do was I would put the data down here. So I want to add the, oops, what's going on with you numbers? This might be harder to see just because the numbers are so small on this screen. Can I make this, I don't think making this bigger helps you at all. Is there a way to change the font size? No. I can hold on errors, HALD. Anyway, so down in location 40, I can put the number 05. And down in location 42, I can put the number 07. And I want to add 5 and 7 and get 12. Okay? And then way up at the top, I would start putting in the instructions that I wrote down before. Okay? And so this is okay. So 1040 as the loading, and so they'll tell you in English what's going on in the instructions. Okay. This is the slowest and most painful thing I've had to deal with in a long time. Man. And now instruction 0 has fallen off the screen. Fantastic. All right. Then 1142 loads register 1 with parent factor 42. Then we have the adding 5201. That was the add instruction I had. Then I have the store instruction 3244, the one I wrote down. Then I have my C000. So this is now a program ready to run. I've got the program instructions in memory starting at location 0. I've got the data for my program down in spots 40 and 42 like I was asked to do. And then I can either hit the run or the step button. If I hit the run button, it walks you through all of the steps one at a time automatically. And then I'll go down to the bottom at spot 44, and I'll see 0C00. Remember, this program is doing things in hexadecimal, and in hexadecimal, A is 10, B is 11, C is 12. So in hexadecimal, 7 plus 5 is C. Okay? So what the lab's making you do and what the homework's making you show me is how you understand what these instructions are and how they do things and how they build programs and how the computer steps through all of the instructions one at a time until it gets to the end, doing what you tell it to do. All right. So far so good. This is kind of where the beginning of the lab wants you to go. Now, obviously, the lab is making you do more stuff and more complicated instructions, but it's all the same basic idea. All right. So what I want to do, well, I guess I'll wait a second, see if anybody has anything they want to ask or say or anything first before I go on to kind of showing you the harder machine language instructions. Where do the extra zeros come from? Zeros. Remember, so the way it works is because the memory of the machine language goes up by twos. When they throw something in there, they're filling. So location 44 was 0C. Location 45, because they go up by twos, is the 00 next to it. And so when they fill the space, they just decide to explicitly say there's zeros in that next spot. It's kind of weird and confusing. I don't know if this is any better to see. Let me show you the other way to look at the memory. So here's the machine again. If you click the tab on top from memory list to memory matrix, it shows you every single address. And so since they're two-digit things, the rows on the left are the first digit, and the columns on the top are the second digit. So you can kind of see here is row 4, column 4, and this 00 is row 4, column 5. So they just fill that because they feel weird leaving half of the two things in their list empty. You can see they even changed my the stuff that I put into location 40 from 05 to 0500 for that same reason. They just didn't want to leave it blank for whatever reason. But empty is the same as 0, and so it's essentially the same thing. So because they're weird and want to confuse you, I guess. Yeah. All right, cool. Any other questions on this stuff that we're doing so far? I'm going to do more examples of this machine language stuff in a second, so I want to make sure you get the easy stuff before we go on to the harder stuff. All right, so let me go back to black. Couple more complicated commands. As I say in the lab, there is no subtract machine instruction. There's add, it does not subtract. There is no. So, all right, that's okay, because adding, as you saw in the homeworks, subtracting is just adding the minus. There is no negate machine instruction. So there's no single instruction to make a number negative and choose complementify it. So you say, all right, I know how to negate something and choose complement. It's flip all the bits and add 1. There is sort of a flip the bits instruction. So the lab walks you through this, but I want to tell you about it just because it's weird. Um, so um, instruction 9: flip the bits of a register if you set it up right. 9 is the instruction. The second number is just like add, the register that holds the place we're putting the answer. So for add, it was 5 whatever, and the second 5 3 5 2 1 5 2 0 1. The 2 was the place to put the sum. The second register is usually the place the answer goes into. Okay. The third register is the register whose value we want to flip. And this last one is annoying and weird. It's the register, or a register, that has to hold the value FF. In the lab, I tell you to put the value FF in register F because I think having all of them say F will help you remember it. But the point is, it's your job to put the FF in the register. Okay? The instruction 9 doesn't work correctly unless you have a register that has been preset by you to have the value FF in it. Okay? So in English, here is how I'd negate the value in register 1. So pretend that we're halfway through a program and for whatever reason we've gotten some value in register 1 that I want to 2's complementify and make negative. Okay? So this is a part of a program that would happen in the middle after register 1 got set up with the value. Okay? I would put the value FF in register F. I would flip what's in register 1, putting the result in register E. Why E? Because this is something I'm only going to need for 1 or 2 lines, and because the registers 0, 1, and 2 and stuff usually hold values I'm working on for the rest of the program. You can use whichever register you want for this. I tend to use the low-numbered registers for stuff I got out of memory and I'm using for real stuff, and the high-numbered registers for things that I'm planning on getting rid of here in a second, or temporary things that I'm using in my negation, because negation is so weird. Now remember, 2's complementing is not just flipping a register or flipping a value, flipping the bits. It's flipping the bits and adding 1. Okay, so I'm not done yet. Put the value 0, 1. In register 0, 1 in register D. That's going to be the one I'm adding for add registers E and D and put the sum someplace. This sum is the negated value. Okay, so it's a long. It's. I mean, think about this. This is a whole lot of steps to go through just to minus a number, right? So machine language again is pretty low level, and the instructions are pretty simple. It's just that computers can do these instructions millions of times a second, which is why computers are so fast. But everything devolves down into something this simple. So in machine language, the first thing I did was put the FF in register F. It turns out instruction 2 puts a value in a register. Instruction 1 copies a value out of memory into a register. Instruction 2 copies a number into a register. 9E1F. So the first instruction loaded the value FF into register F. The second instruction did that flippy thing. Remember, instruction register F has the F, the FF value. The 1 is the register I want to flip. The E is going to hold my flip value. And then I'm going to put a 1 in register D. And then I'm going to add register 2 holds the negated value. So if that went too fast, the lab walks you through this as well. I just wanted to kind of talk you through it. But the point is, first of all, it only works if you set up register F with the right value beforehand. And don't forget, negating is flipping the bits and adding 1. So don't just do one or the other without doing both. Okay. Questions on that? Negating a number? All right. So the other big complicated thing the other complicated instruction changes the program counter. Remember, the program counter was a special register that held the address in memory of the instruction I wanted to do next. Okay, and so up until now, every single instruction starts at the top of the program at address 0 and then goes down line by line by line until you hit the C or you run out of instructions. Okay. The idea here is we have algorithms that want to do steps sometimes, right? Some of you for the COAT algorithm for the homework said stuff like, well, if the code is already zipped, then you need to unzip it, right? And if you don't, you don't, okay? So we want programs that have steps like ask a question and then either the question's yes or no, and then based on the answer, we do something if it's yes, we do something else if it's no, and these somethings or something else's in machine language terms are different instructions at different lines of your program. Okay, so so this leads us to our machine language has an instruction B. Remember, these are hexadecimal, so B means 11, but you would type B because everything's hexadecimal. Okay, B, the second, I won't use 0, that's a bad example. Something like that, B108. The second register is a register we compare against register 0. Always compared against register 0. Okay. So B1 means we're going to compare register 1 versus register 0. B7 means we compare register 7 against register 0. The thing we're comparing against is always, always, always register 0. Okay? The 08 is the value we set the program counter to if the registers we are comparing have the same value. So the idea here is the values of the program counter to the registers we're comparing have the same value. So let me rewrite B108 again. Here's what B108 does. Okay. First, compares the values in register 1 versus register 0. We're comparing register 1 because the second digit is 1. We're comparing register 0 because the B instruction always, always, always compares against register 0. Okay. Second asks, are they equal? If yes, set program counter to 08. If no, leave program counter unchanged. And so now, after you see a B instruction, you don't know what instruction is going to happen next. Okay, it depends on the values in the thing you're comparing and register 0. If they're the same value, the program counter changes, and you jump to a very different part of your program, probably, instead of doing what's next. If they're different, you do what's next like normal, and basically the B instruction did nothing. Okay, so this is how we're going to do what I was talking about back here. Ask a question. If the question's answer is yes, do something. If the question answer is no, do something else. The question is, are they equal? And if they are, we'll do the thing we'll do the instruction at the address we're going to. And if they're not, we'll do the instruction at the address that's next. That's the point of the B instruction. I guess I'll say also while I'm here, the B instruction can also be used to return to a previous instruction to do it again. So one of the things I walk you through in the lab is an algorithm or a program to add the numbers from 1 to 10. And so the basic algorithm is put a 0 in a register, put, let's say register 0, put Put a 0 in register 1. I forget what registers I use. Put an 11 in register 0. Put a 1 in register 2. Register 1 is going to hold the total. 11 is when I stop adding. And register 2 is the number I add next. So the basic algorithm is going to be add whatever's in register 2 to whatever's in register 1. Register 1 is going to accumulate an answer, and then if I dink up register 2 by 1, I'll add 1 the first time, and 2 the second time, and 3 the third time, and 4 the fourth time, and 5 the fifth time, all the way up until register 2 is 11, in which case I'll stop. Okay? Add register 1 to register 2, put result in register 1. So add the running total to the current number I add next, put the total back in the running total, and then add 1 to register 2 to get it 1 closer to finishing, to make it hold the next number. And then here's my question. Is register 2 equal to register 0? If yes, go back to here and add the next number. Or sorry, I thought that was wrong. If yes, sorry, go. I got my jumps backwards. Go to end. If they're not equal yet, go backwards. And the place we go back to is, again, here to add the next thing. And then if I ever go to the end, that's the end. So the point of this is not to make you understand my babbling right now, okay? I think I explain this a lot better in the lab itself. The algorithm, I walk you through every single step of the machine language, and I show you what each one does and how it all fits together and that kind of stuff. The point is to get you kind of thinking about the fact that there exist instructions that mess with the machine, with the program counter, and you'll need those to have programs that ask questions like, should I do this again, or should I do this choice or that choice, or something like that. Makes sense? Any questions on this? Again, if you've seen it in the lab, hopefully this is helping you clarify it. If not, hopefully you're ready for the lab now. So any questions on something you want me to explain to you before you dive into the lab and homework and I won't see you for 5 days? Have I thoroughly baffled you? Is this, are these explanations helping you or confusing you? Or both? Okay. Good. That's good to hear, at least. So really, really try to start the lab early if you can. Really, really ask me lots of questions when you get stuck. Again, the lab that I put up there is two-hour days in the lab of the regular semester class. So expect to spend about that long getting through it, and and it's even more than that probably, because in the face-to-face class, I'm walking around the lab helping people when they're stuck. Here, you have to come find me when you're stuck and ask me questions by email or whatever. So make sure you do that, okay? If you want me to, we can set up a time on the chat and we can share screens and talk to each other. If you want to just send me screenshots or export your programs to me, whatever helps, okay? But You want to make sure you leave yourself time for me to help you. This is probably the hardest homework of the semester, at least in terms of having to learn and understand a new thing. The homeworks that are coming up in the next 2 weeks, I think, are less hard to understand what you have to do, but they're probably more time-consuming things to do, if that makes sense. So don't get frustrated if this feels hard and complicated and how do I understand all these bizarre numbers, because, yeah, it's hard. So don't freak out. All right? Any other questions? All right. If not, good luck. Work on it. Try your best to figure it out. Ask me lots of questions, and I'll see you next week when we're going to do totally different stuff.